In this video, we're going to talk about the basics of logistic regression. First, let's start with an overview. We start with the goal of logistic regression. That is to estimate the posterior probability. To get to these estimates, we will discuss how to turn real numbers into probabilities. That will lead us to the cost function of logistic regression. And we discuss how to train this model with stochastic gradient descent. Finally, we talk about how to make predictions with logistic regression. We will use an example where we try to predict the probability of paying back a loan. Note, to default means that you cannot pay back your loan. In logistic regression, we want to know the probabilities of these classes. What is the probability to pay back the loan or to default given the features? Okay, how do we write these probabilities? The posterior probability to default is written as P y equals default given the value of x. Here, x would be the value of the balance. X can also refer to more features that we may have measured. We are interested in this probability, the probability of a particular class given the features. This probability is called the posterior. Using logistic regression, we are going to approximate these probabilities. Furthermore, in logistic regression, we want to use a linear model. The predictions of a linear model can be written using the formula on the slide. However, these predictions cannot be interpreted as a probability because it is a real number. It can be negative or larger than 1. So, how do we turn a real number into a probability? If we can do that, we are already one step closer to our goal. To transform real numbers into probabilities, we will use the logistic function. We will indicate this function using sigma. The formula is given on the left. On the right, we have a plot of this function. You see that if you apply the function to a large negative number, it will be close to 0. If you apply it to a large positive number, it will be close to 1. In between, it goes in this S shape from 0 to 1. The output of the logistic function is a probability because it's always between 0 and 1. Let's look at some examples in the table. Say our linear model predicts -5. Then this translates to a probability of 1%. If we take 2, we get a probability of around 75%. And if we take 2.5, we end up with a probability of 95%. So this is how we're going to turn numbers of our linear model into probabilities. We take the predictions of our linear model and put them into the logistic function to get the probability. The idea is that this should approximate the posterior probability. To come to the cost function of logistic regression, let us look at an example. In this example, we have 3 persons, A, B, and C. We have the output of our linear model and the corresponding probabilities. These are the posterior probabilities estimated by us of these people defaulting on their loan. Now we also know what happened in reality to person A, B, and C. We see that person A defaulted, person B paid back the loan, and person C also defaulted. Now we're going to assume that the variables x and y for person A, B, and C are independent. This means that the loans of A, B and C are not related. Now I have the following exercise. Compute the probability that person A and C default and person B pays back the loan, given their features. You have all the information you need to compute the answer. You might have to think back to your statistics class. How to combine probabilities. Pause the video and try to come up with the answer. Okay, let's discuss the answer. Since the persons are independent, these events are independent. This means we can split the big probability into these individual probabilities and multiply them. That was the first step. Now let's talk about the second step. You should realize that the values for the probabilities A defaults and C defaults are listed in the table 0.01 and 0.95. The only probability that we don't know is the probability for person B, who has paid back the loan. How do we get the probability of paying back the loan? Well, you should remember that all posterior probabilities sum to 1. So if person B has a probability of 75% to default, then the probability to pay back the loan is 25%. This way we get the answer given on the bottom of this slide. What we have computed here is the probability of observing this data. Note that in this example our model predicts the probabilities reasonably well, except for person A. Here we predicted a probability of 1% of defaulting, yet this person defaulted. If you multiply all these probabilities together for the y's that you observe, we obtain what is called the likelihood. This is the probability of observing the y's of the training set according to our model. Since this is exactly the training data that we observe, what we want to do is we want to maximize this probability. If we see a person is defaulting, we want that the posterior probability for defaulting for that person is large. If we see a person that pays back their loan, the probability of defaulting for that person should be small. The likelihood multiplies all these probabilities together, that should be large. Thus, logistic regression wants to maximize the likelihood. In practice, people instead minimize the negative log likelihood. Okay, so what is that? Below, we have the likelihood that we have seen before. We multiply all probabilities together. The negative log likelihood, also abbreviated as NLL, is the negative log of the likelihood. If you have something that is multiplied together and you take the logarithm, the multiplication turns into a sum. And here we now have the sum over all these probabilities. The minus sign is there to turn the objective function into a cost function. Instead of maximizing the likelihood, we want to minimize the negative log likelihood. The minus log of each probability of each training object is called the log loss. You want the sum of all losses to be as small as possible. Why do people use the negative log likelihood? Well, because it is a sum, it is more numerically stable. Because if you multiply many small numbers, you get all kinds of rounding issues with your computer. However, if you sum small numbers, this behaves much better. So that is why people use the log loss. Now let's have a look at this log loss in more detail. Imagine we have an object with a positive label, y equals 1. On the x-axis is the predicted posterior probability of the positive class by our model. On the y-axis, we visualize the value of the log loss. On the left, the predicted probability for the positive class is 0. But this must be wrong because we observe the label +1. In this case, the log loss is infinite. This is the case if the predicted probability is wrong and certain. By certain, we mean that the predicted posterior is close to 0%. The larger the posterior probability for the positive class, the smaller the loss. Why? Well, because for this sample we have observed the positive class. Therefore, the posterior probability should be as large as possible for this sample, and this is encouraged by a small loss. If the probability for the observed label is 100%, then we see that the loss becomes 0. So we get 0 loss if the prediction is certain and correct. Now we have all 3 ingredients for iterative training. The first one is the model class. In logistic regression, we use a linear model. As a cost function, we use the sum of the log loss over the training set. This is the sum of the log losses. Note that the cost function j depends on the parameters of the linear model. Because the posterior probability comes from the linear model. Depending on the observed label, we plug in the right probability for each object in the sum. This cost function determines a loss landscape in terms of the parameters w. This objective function is very smooth, and one can even prove that there are no local minima. So we can use gradient descent. There is only one downside. For gradient descent, we need to set the batch size, the learning rate, and the number of epochs, and we should scale our features. If you're going to use logistic regression, you must carefully tune these hyperparameters. Now that we have discussed how to train the model, let's discuss how to make predictions. Let's look at an example. Let's say we have trained a logistic regression model that predicts if a student has cheated on an exam. My model says for a particular student that the probability of cheating is larger than 50%. Now my question to you is, should we accuse this student of cheating? Yes or no? Please take a moment to think about this, pause the video, and afterward we will continue. Okay, welcome back. The answer is no. We don't want to accuse this student of cheating. 50% is not a very high probability, right? We only want to accuse a student of cheating if we're very sure that the student is cheating. So we only predict cheating if the probability is larger than, for example, 95%. To conclude, to come to a prediction, we check if the posterior probability surpasses a threshold that is set by the user. Okay, let's summarize this video. Logistic regression approximates the posterior. We use the logistic function to turn the predictions of a linear model into probabilities. Furthermore, we have seen how to derive the likelihood, the probability of the training data. We discussed that the logistic regression minimizes the negative log likelihood. Logistic regression uses gradient descent for training and therefore requires careful tuning of hyperparameters, and we need to scale our features. Finally, to come to predictions, we can set a threshold that determines when we are going to predict a certain class.